So we're going to talk about contact functions between cells in PhysiCell. And so the goals here, we want to introduce the notion and the syntax of contact functions. We want to point out a particular class of built-in functions, contact functions for spring-like adhesions, and then close with a couple of examples combining some of the concepts from yesterday and today with the contacts to form multicellular little worms that crawl around on the screen. So first, let's talk about how you would attach cells, because you need cells in contact to be able to evaluate contact functions. And so PhysiCell has a few functions. First, there's a member function called attach cell, and it says, who do you want to attach? Add me. Well, PhysiCell will add me to the cell's data structure of attached cells. And also, this is a symmetric operation that the cell that's calling it will add this target cell, but then that target cell will also add your cell. So the two will be attached in both directions. So both cells know about the attachment. If you're not attached to if you're not running as a cell method, there's just kind of a global function called attach cells. Say, cell 1 and cell 2, you pass their memory addresses and it will attach cell 2 to cell 1 and cell 1 to cell 2. And it's symmetric. And these operations, we worked hard to make sure that the thread's safe. So you can put them anywhere in PhysiCell, whether you're inside of an OpenMP loop, and it should be no problem at all. And once they're attached, every cell will have a vector of memory addresses called cell.state.attached cells. And it's going to be a vector of all the attached cells that you yourself have attached. There is no other function in PhysiCell that touches this data structure. So this is completely yours and yours alone to manage, which means you should have full knowledge and control of what's going on to that data structure. And if you want a quick way to assess how many cells are attached right now, of course, you could just, it's a vector, it's standard vector. So you can do cell.state.attached cells.size. That would get you the number of attached cells. Or you do cell.state, and there's a method called number of attached cells, which just quickly calls that syntax. Now, if you want to attach cells, you also probably want to be able to detach cells. And so you can call the method function detach cell and the address of the cell you want to remove, and it will remove it. Oh, I should point out also that attach cell does a quick check to make sure that the cell you're trying to attach is not already attached. So you won't have like 5 copies of the same attachment. So that's a safety that we've added into that. Detach cell will say, well, first of all, make sure that it has been attached, and so remove it. And it's going to remove it symmetrically, that you will remove cell will remove you, so the separation is complete. Then there's a method that's not in, this more global, it's not in the method, just detach cells 1 and 2, and it will again do this thread safe detachment of the 2 cells. Another method that's handy is, you might want to quickly clear out all the attachments of a cell. And so there's a function called remove all attached cells that will basically run that detach function for all the connections. So, and these should all be thread safe. Some quick notes. We thought it was ambiguous what to do with attachments when a cell divides. So when a cell divides right now, it removes all attachments. So you're going to need to do whatever your model is to reform your attachments after cell division. And death will automatically remove all the attached cells at the end of the death process, basically through the destructor function. So it'll be like the very last thing that the cell does before it leaves its, shuffles off this mortal coil, will remove all of its attachments. So that should be fairly automated now. Just kind of an example of this is, imagine you have some kind of custom function, evaluating at the mechanics time step. And that has, your standard, syntax of your cell pointer, your phenotype, and your time. And what you might want to do is say, go into the neighbor's data structure, which is created by the potential function. So you have a list of all mechanically interacting cells. And you are going to say that if any of those cells are close, we're going to attach them as long as I don't have more than 6 physical attachments. And so I'm just going to go through my vector of state.neighbors of all possible mechanically interacting cells. And I'm going to iterate through them and say that if, I'm going to calculate my displacement and then my distance using the built-in norm function we talked about yesterday. And if that norm is under some threshold, let's say the sum of my 2 cell radii, and if I have fewer than 7 attachments or up to 6, I guess I'm going to go ahead and attach cells. But actually, now they think about it, probably I really actually want to have, well, that's fine. And that's it. And also, just for the fun of it, I'm going to add a little bit of chemical communication, say that I'm going to sample some diffusing environmental signal called signal. And if it's above some threshold, I'm going to remove all the attachments. So this kind of gives an example of this. Why is the maximum number of 6? Because I arbitrarily decided for this example that the number would be 6. There's actually nothing attached to it at all. But for our cells in the hexagonal, like in 2D, that might be a good, sensible thing to choose. So, and Daniel Roy asked a good question. So the cells do remain attached while the dead cells are shrinking or shriveling? Absolutely. But if you want to, you can remove the attachments earlier, and that's not a problem at all. You could, for example, put this into your phenotype function. Say that if my cell is dead, call the function called remove all attachments. Because one thing we do know when you watch apoptotic cells in particular is that they basically fall up and start shrinking, which means that that they're not attached to their neighbors. And so that's something you do see. And then, of course, they blub off their cytoplasm and stuff. So you may want to remove your attachments earlier, but we didn't want to assume that for you, right? Necrotic cells, on the other hand, do stay attached to their neighbors for a long time. So we didn't want to presume that for that. So those are really wonderful questions. Thank you. So let's talk about that. So now we have a way to attach cells and detach cells. Contact functions will operate on the cells that you have decided to attach. So if cell A and cell B are attached, they can interact by their contact functions. And we'll talk about the syntax of that in just a second here. But I do want to give a warning that the contact function evaluations are placed in an OpenMP loop. So you need to be careful to be thread safe when you write these things. So the idea is that, A will have a contact function, B will have a contact function. So let's say that A is evaluating the contact function. So A is connected to cell B. It runs this contact function connecting A and B. A writing to A is thread safe. A writing to B is not, because some other cell could also be interacting with cell B and writing to that cell. So by convention, what you want to do is do writes to A is safe, writes to B is not safe. So if you want to do a write to cell B, the other cell, then put it into a pragma OMP critical to make sure that's a thread that basically takes it temporarily down to single threaded and says that it can't have two threads entering at the same time to keep it thread safe. And so every cell then has its own contact function as a member of the functions data structure. So cell.functions.contact function, and by default, it's null. So, PhysiCell will say, well, if that's a null pointer, there's no function to evaluate, we won't even bother going forward with trying to do contacts. But if it does, then PhysiCell will loop through all the cells as part of the standard OpenMP loop and say that if the cell does have a contact function, then it's going to evaluate the contact function against my cell, the cell that you are, and the cell in the connected, actually, it's not in the neighbors, it's in the attached cells. Let me fix that. So let me, this is a typo. So I have a few slide decks I need to re-upload later with some corrections. So what I'd like to do is to start putting this into a real example. But first, let's talk a little bit more about, that's the concept of the contact functions. Now let's talk a little bit about their syntax. So contact functions are more or less a variation of their standard function syntax, but because we have two cells, we need to increase the number of arguments here. We have cell A pointer and its phenotype, cell B's pointer and its phenotype, and then the double delta T of amount of time we want to push this model in the case that you need that. And so generally speaking, cell A is going to be the cell that calls the function, and then it's going to test its interactions against the cell B that's in its interaction list, its attachment list. And so that's what we have. Often A, and I also want to point out, right, that if A and B both have the same contact function, that means that A will kick off this function once, and B will also evaluate this function. So you need to think a little bit so you don't double count your interaction. And so just be mindful of that when you write your interactions. But you can take advantage of that, right? So remember we said that maybe there's some interaction needs to write to both A and B. Well, when A evaluates it, let A write to A, and when B evaluates it, let B write to B. Both of those are thread safe. So that's a little bit faster computationally and gives you kind of a way to get your head around the interaction. So this can be confusing. That's why I wanted to kind of push this one off to the end when you got a little bit more experience at PhysiCell. We do have one standard contact function called standard elastic contact functions, like a spring, basically. And so it has the standard syntax. This is in the standard models. In PhysiCell, you don't have to include anything. And the idea is that we are going to more or less say that when cell 1 evaluates the contact function, it's going to pop into its mechanics in its phenotype and grab the elastic attachment constant and multiply it by the displacement. And so it's like it's basically applying a spring-like force that contributes to the cell's steady state velocity, pulling it towards cell number 2. And because it's only acting on itself, that's a thread-safe operation. Then when cell 2, remember cell 2 is also attached, when cell 2 gets around to evaluating this contact function, it's going to perform the exact same computation, but now say adding to its velocity, it's going to multiply its spring constant times the displacement towards x1, and it's going to pull cell 2 towards cell 1. Now, in physics, you're generally speaking like forces to be equal and opposite. So this can only happen if E1 is equal to E2. There are ways to fix that where you could kind of come up with an effective elastic modulus based upon the two differences of things. That's probably something that we should fix in a future version of PhysiCell. For now, you probably just want to have them have the same spring constant. And so again, kind of apologies for that limitation right now in the current implementation. There's probably a variant we could build in the future that would might be have like a resting spring length so that you would kind of scale this a little bit differently, but that's not the default standard function right now. And so let's put this together and build a basic example of kind of forming a worm-like structure. First, a really basic one. And so the idea here is that we want to grow a chain of cells or a worm. And so we're going to have a bunch of cells independently wandering in space. And this is kind of like the beginning of a slime mold, that they are secreting a chemical factor. They're going to migrate up towards that chemical factor to start aggregating. And when they get close to each other, they're going to test for contact with an interaction distance and say that if I haven't exceeded my maximum number of attachments, which is something that we are arbitrarily going to choose as part of our modeling process, then they will form an attachment and keep track of that. And once they're attached, we're going to give them the elastic spring-like adhesion contact function. And we're going to do one last thing then. In our custom rule, we're going to say that if the cell has one attachment, they're going to try to basically stretch themselves out by wandering away from all the other cells. So they're going to migrate away from grad S and increase the secretion rate of their signal just to kind of show that they're boss. And the cell has more than one attachment, then so if they're one attachment, they're basically at one end of the growing worm. If they have more than one attachment, then what we're going to do is we're going to slow down their migration. In fact, we'll turn it off and decrease the rate of secretion of S. So the high levels of S will kind of say that anyone that's not attached is going to be trying to move towards the heads or the tails. Really, there's no difference right now. And anything in the middle is going to say, I'm going to just stop and be elastically attached. So let's go through a full modeling workflow. We want to plan the model, which we kind of did, but let's sketch it out a little more. Populate out the template project. Then we're going to use the model builder GUI to kind of set the basic properties of this model. And then we're going to build our custom functions in C, put it all together and give it a go. So Daniel Roy asked a really great question. These velocity updates take into account the mass of the cell. Right now, they don't, for the following reason. We are using an inertialess approximation where you have a force balance law where you have basically mass times change in velocity or acceleration equals the balance of the forces. And one of those forces is drag-like terms, which would be basically just proportional to cell velocity. In the inertialess assumption, you assume that the cell forces come into a balance relatively quickly, which is true in a fairly lossy drag draggy environment like something fluid-filled. And so like Dirk Drasdo went through a lot of great calculations of that about like 15, 20 years ago. And so we just kind of relied upon that as a boundary assumption. The good news then is if you're in the inertialess assumption, mass times acceleration is 0. And you can divide by the drag-like terms to get a direct solution for cell velocity. But notice that once you do that, mass drops out altogether. So mass doesn't affect the steady state in this particular, inertialess formulation. That's something that could be improved in the future, but right now it's not in there. The good news of that is that we can solve directly for cell velocity, so we don't have to solve a second order ODE for cell acceleration in this kind of a formulation. But the bad news is you're right, we don't fully account for the masses. And you know, in some sense, right, well, you have equal opposite forces, but like if you have one cell that's huge, one cell that's small, they probably don't want to have equivalents. You should be conserving momentum as well as just the forces. And so that would probably change some of that. So that's, I think, an area that could use some future refinement. It's a really good question, Daniel, and it's actually quite a deep one about the framework. More or less, we're kind of, when the cells are comparable sizes, works out pretty well, but if they're absurdly different sizes, we may need to rethink that a bit. Let's get into the modeling workflow. We're going to plan our simulation. We're going to have a smaller domain with 3,000 minutes max time. And actually, I'm going to change this a little bit. For the early model, let's just do 720 minutes. That's probably enough. Actually, even 1440. We'll make it a little bit faster. We need diffusion coefficient with diffusion coefficient 100,000, kind of comparable to oxygen. Length scale, let's make 10, decay constant 10, so that when you take a root of d over lambda, you get 100 microns length scale, so kind of an intermediate communication distance. Let's go ahead and turn on the virtual wall so cells don't leave the domain. And really right now, all we need is one custom data, is the maximum number of attachments, which I'll default to 2 because I want to form chains. And then I'm going to do one cell definition for worm cells. And let's see here. And let's see, now we'll talk about this, the worm phenotype. We're going to set the cycling rate to 0, apoptosis cycling, and secretion rate to 10. So we kind of have a good substantial secretion signal. We'll turn motility on with chemotaxis towards the signal with kind of really fast responsiveness and just very biased migration for this. We're just going to make it deterministic, basically. And then we're going to have the custom migration rule that if the cell has 2 or more links, we'll set the migration speed to 0. If it has 1 link, we'll just change the direction of motility. No phenotype rule, because the cells are not going to be cycling. We don't really worry about that. And then the custom rule will just say that we're going to look for cells to attach if I don't have maximum number of attachments yet. And if I find something, attach it. And then we'll update the migration rules based upon the number of attachments. And the contact function, just use the spring function. And we'll go ahead and modify the coloring function too, that if the cells are unattached, they'll be gray. If they have 1 attachment, they'll be red. That could be either a head or a tail. They're the same for this. And then if they have 2 attachments, they're going to be blue. And if they have more than 2, which won't happen today, they will color them yellow. And then lastly, I'm going to make we'll create cell types to use the custom functions and modify main to make the custom coloring. So we'll kind of go through this entire full workflow. So let's go ahead and just start kind of in our standard way. Just in case, I'm going to type make reset to kind of get back. Oops, well, maybe I could use some rest, but make reset to get us to a clean slate. Then make template to populate in the template project. I'm going to type make one more time just to start compiling that project. And now, while that's running, I'm going to go and open up the model GUI, the model builder GUI. So Python, I'm going to run this from inside of my config directory so that I will know that my config file will be storing directly in this directory here. So I'm going to call it up here, and I've got my template opened up here. I'm going to shrink my slides so I can kind of put my slide deck on one side and the model GUI builder on the other side, just so I can really get a quick, clear view of what I'm trying to do. So first, let's go ahead into the domain or the config basics tab, and we're going to edit our domain. It looks like I've been changing this even as I've gone through writing my slides here, but let's make the domain negative. Oh, actually, I'm going to leave the. Well, I have a bit of a contradiction in my slides here. Let's just leave the domain alone then, and I will go back to my planning and make this self-consistent. So I will release an update on my slide deck later. And I'm trying to think if I ever added that, but I think that was the only place I specified the domain size. And so let's see here, we'll go into the modeling. We're going to make this a 1440-minute simulation. I'm going to turn all my virtual walls over here so they don't leave the domain. I've got 8 threads on my computer, so I might as well do 8-threaded. I'm going to save my data every 360 minutes. And I'm going to save my SVGs every 10 minutes because I really watch the cell migration in this. Let's see, and I think that's all that I need here on the domain. So the next slide, let's work on the microenvironment. I'm going to rename the substrate to signal. So that's a signal, chemical signal released by these cells. I'm going to leave the diffusion coefficient at 100,000. Decay rate looks like 10 is good. Initial conditions and Dirichlet at 0 looks pretty good to me, so we'll leave that as it is. Now let's go to the cell definition. So we'll go to cell types, and we're going to rename the default type to worm. So we have a worm cell over here. So I guess we're doing nematodes today. Michael Eisen maybe has got his ears tingling or something because we're doing worms today and not flies. So let's see here. Let's rename this to worm. Let's go to the cycle tab, and I'm going to choose the simpler live cell model. And I'm going to choose the transition rate representation. And I just want the transition rate to be 0 because I don't want to worry about birth and death in this model. And then I'm going to go to the death tab and change the apoptosis rate to 0. So there's no birth and no death in this particular model, just to keep it simple. We want to focus just on the interactions for now. Now we're going to go into continuing the phenotype modeling. We're going to leave volume alone. I'll leave mechanics alone for now. Let's look at motility. And let's see here. We want to have the speed of 1, and whatever this word is, probably should be persistence time. Persistence time we'll leave at 1 minute. Let's turn the migration bias all the way up to 1, so we have deterministic motion. Don't forget to turn on motility. So we'll click this button here to turn it on. And now, what kind of motility do we want? We want chemotaxis. So let's enable chemotaxis and say that we want to be going towards the signal, which is the only diffusing factor we have, and towards it. So that should be good on cell motility. And now we go to custom data. And I'm going to rename this, this first custom data to max attachments. And let's have a default value of 2. And I'm going to go into user parameters, and I'm going to change the number of cells to 500. But that should be it. Let's go ahead and save this. And you know what? I'm going to actually take a brief pause. And let's run the project without the custom rules and see what we got. So make, we got that. We type, project in our config file, which is mymodel.xml. And let's just run this thing by itself. And we're going to go into the output directory. So let's see here. Where am I? Here's my PhysiCell directory. I'm going to go into output. And let's just see what this thing does by itself before we add the custom rules. So here's my initial picture, a bunch of cells. They're all gray because they're unattached, randomly seated in this millimeter by millimeter domain. And if I just kind of scroll through, I'm going to just pick another time. I'll sort by type. That makes it a little bit easier. Let's find a later SVG file. Maybe. I know they're in here somewhere.
I believe you stored SVGs every 360 minutes.
Oh, crap. That's not good. Thank you. Yes, no wonder there's so few and there's way too much data. Let's go ahead and cancel that. Thank you for catching my error. Let's change this to SVGs every 10 minutes and full data every 360 minutes. This is a good reason to leave your model builder open because we can easily make a fix like that. So let's make data cleanup, clean up this mess I just made, and run the project. So another good reason to actually run your model before you start adding all the C++, just to make sure there are no little surprises like that. There we go. Oh, that's much better. Thank you. Yeah, so here's a picture a little bit later on. They're all gray, right? Because we don't have any custom functions yet. They're not attaching. But we should start seeing them aggregating, hopefully. Oh, that looks awfully frozen. So I'm a little concerned that we have something not quite right. So when in doubt, we are going to open up the actual model file. I'm going to browse through this just manually, make sure there's nothing amiss. We have something called signal in the environment. It's diffusing with coefficients that we expect. Cell definition worm. Let's go into motility and see what's going on. We have persistence time. We have migration. It's enabled. Ah, I forgot to turn on secretion. That's the other thing that's missing. Okay, well, this is a really great argument for running and building models incrementally. We forgot to go into the cell types, into the secretion tab, and we forgot to turn on secretion. Of course, they're not aggregating. There's nothing to aggregate to. That explains a lot. Okay, so we saved that. Notice now when I reload my config file, I've got the secretion here. So let's go ahead and make data cleanup. And we actually change the code, so there's no need to recompile, and we'll just run it. And while that's running, let me take this quick question. So Robert Moore asks, can we make the agents change phenotype based on the strength or the amount of time of the attachment? That could be useful for lymph nodes. Absolutely, yes, that's a really cool idea. What you could do is you could add a custom variable to the cell that says aggregated attachment time. And then in every delta t, when you evaluate your contact function, you could evaluate the spring function and then add a little tiny delta t to that connection. Now, if you have, I suppose what you really want to do is you want to make, you probably want to keep track of the time of the connection for each of your connections. Now, PhysiCell does have something that's not as, it's actually, if you go into the user manual, you can find this. It's not in any of our tutorials right now, but you can also make something called custom vector data for a cell and keep track of a vector of custom data. So you can make a vector called attachment lifetimes, and you can make sure that that always has the same length as your attached cell vector. And so you can kind of go through that and incrementally update all those as you go. So that's a possibility, a distinct possibility. The other thing is you can think about Poisson processes, right? If you want something to be proportional to the area under the curve, then that is equivalent to saying that your probability of doing something is proportional to delta t. And that as you go on, the mean time to some event happening is proportional to 1 over the rate. So your probability would be rate times delta t, the probability of some event in between now and t plus delta t. 1 over the rate is the mean time, the expected time you have to wait for that event to happen. So you automatically get something that's proportional to how long you've been attached. So that's actually kind of a nice trick when you use rates in a stochastic model. Okay, we've got data. Let's see what we got here. Let's type make GIF, make an animated GIF, and in the meantime, let's pop open some of these snapshots. So here's my, let's look at initial. Here's my initial one. Let's look at snapshot 10. And we see that we've already formed really nice clusters. So the cells are aggregating really great. This is like an example, very similar to Ava and Michael's examples yesterday of quorum factors. Our signal's acting like a quorum factor. And it's actually kind of neat, right? Completely in XML, nothing else. We're already able to write cell aggregation just with the built-in chemotaxis and secretion of a chemical factor. So I get a kick out of this, that it's so easy to write models like this now with the model builder that Randy created. And now we're just going to fine tune that behavior to make them do something more interesting. But already we've got cell aggregation with just a few minutes in the GUI. So oddly enough, we're waiting too long for this animated GIF. Oh, we got it. Let's take a peek here. Yeah, you can see all the cells are basically aggregating. Now, over time, I'd expect, yep, you see that these clusters are starting to find each other too. And so, yeah, we're seeing that the clusters are now actually merging. So we got to really get this coalescence of the cell populations over time. This is actually really fun. Cool. Man, I would have loved to know this as a graduate student. Okay, so we've got that. And now let's start adding the custom code. So we'll go back to our tutorial. We're done with the model builder for now. So let's just go straight over to the C++. So first I'm going to do is I'm going to declare some functions. So I'm going to go to custom.h and I'm going to declare all these custom functions I'm going to be using in my model. And so here is custom.h. Yes, let's definitely reload it. And okay, I've got these weird characters from copying and pasting. So let's just delete those. Why I like to view all the white space characters. So I've got two functions here that are really just dedicated to managing, migration. I've got a custom function, which is like my mechanics time step, and I've got a contact function. And then I've got a coloring function declared here too. So now let's just start implementing these. So migration rules. Let's go into the custom.cpp. And this is where we're going to modify our functions. So first, let's talk about these migration functions. A stretch migration function says that we want the cells to kind of, at the ends, to stretch outer worms. So we want them to migrate away from the chemical factor. So we're going to change the migration direction in chemotaxis to -1 to go the wrong, to go the other way. And I'm just going to, tweak the speed a little bit. Normally, you don't want to hard code parameters, but this is just a demo. And then if a cell's in the middle, we're just going to shut down motility altogether. Okay, so we got that. And now let's add our custom rule. This is a little bit more complex. Let me paste the beginning of the code here first. And I'm going to zoom in Notepad so we can see this a little bit better. Hopefully this is bigger on your screen now. So my custom function for the worm, this is at the mechanics time step, says, first I'm going to look and see, let's look for any cells we might want to attach to. So I'm going to go and say, how many cell attachments do I have right now using that function we talked about? And I'm going to get a vector of nearby interacting cells. And as long as I have not made my maximum number of attachments and I've not finished searching this nearby data structure, then I'm going to go and say, look at the nearby cell. And I don't want to attach to anyone who is not me. Now, this, remember we said, is already safe, that it's not going to try to attach. So we probably don't need this line, but I put it in anyway, saying, don't try to attach to yourself. Although yourself should never be in the nearby list, I think. But, oh well. Don't try to attach to yourself. Don't try to attach if you have already exceeded, met the maximum number of attachments. And if those conditions don't hold, then this is something worth attaching to. So I'm going to call the attach function, say, I'm going to attach, this is my member function, right? So all I have to do is, I guess I'm going to call the global version, it looks like. So attach cells of myself and this nearby cell. There's no reason I have to attach them in this order. It's completely symmetric. But now they have attached, I'm going to just increase the number of attachments that I'm tracking. So I'm searching nearby cells. If I'm not already full up of attachment sites, I'll form the attachment. Let's see here. And then the next part of the rule, let's copy paste the code, and then I will walk you through it. Say now here's, we just change the motility characteristics. Say that if I have 0 attachments after all this is done, then I'm going to continue using my chemotaxis migration function as my update migration. So this is, remember, the cell functions, migration bias direction is going to be run by the bog standard PhysiCell chemotaxis. If I've got 1 attachment, then I want to use that stretch function we just talked about, and let's go ahead and increase the secretion rate. And if I have 2 more attachments, then I've got to be somewhere in the middle. And so I'm going to just shut down, I'm going to use the middle migration rule and slow down my secretion. Okay, so that's our custom rule. You're going to love this. Here's my contact function. My contact function, oh, this is almost too small. All my contact function does is says, use the built-in elastic contact function. That's it. That's it. So not too shabby. So our contact function is really, really simple right now. We're going to say use the spring function. And then let's modify the create cell types to make sure we're using all these wonderful functions. So I'm going to go here to the very top and look for the create cell types. I'm going to scroll down and I'm going to replace all this stuff here that works in the cell defaults. I'm going to paste in my stuff. So I'm going to look for the worm cell definition. I'm going to set the phenotype rule to null because we don't want them to bother with that. We're going to set the custom rule according to the worm function we just made and the contact function to the worm contact function. And I'm going to go ahead and set in that cell definition the elastic attachment constant to 0.03. Just going to hard code it for now. I suppose we could have done this in the GUI if the GUI knows about that. So let's go to mechanics and see what's there. Mechanics in the GUI right now does not know about this constant. So you really do need to do it in your setup right now. So we will leave that alone. And so now we've made our custom functions. We've made sure that the cell definitions know to use them. Let's make a custom coloring function that we talked about. And And this is a new coloring function called worm coloring. And this is just kind of looking through and saying, look at my number of attached cells and color it gray or red or blue. And if I don't meet these criteria, yellow will be my default. And that is it. And let's see here. Oh, but we should probably make sure we actually use a coloring function. So you open up main and you look for the part where it says cell coloring function. And I'm going to just basically, I'm just going to overwrite that function with my worm function. And I think we should be ready. Let's rebuild the project. So just make, sometimes better without a typo. And now let's do make data cleanup our mess, and type project, which is our executable, config/my model XML, and run it. And let's let it go for just a moment and look at a few of the early times. So here's my initial picture, just like before. 10 frames later, they've already found each other. So maybe we should have output a little bit more frequently, but we probably already have enough to understand what's going on in this model. Let's see, if I have a third window open, I have many windows open. Let's type make GIF and just make an output of whatever, an animated GIF of whatever we have so far. So you just kind of see the dynamics. And I'm not sure what we'll finish first, the model or the animated GIF. We'll see. We can see that they've definitely formed chain-like structures. We have the things at the ends are red because they have one attachment. Things in the middle are blue because they have two attachments. And that's the number of attachments we allowed, so there's nothing that's colored yellow. Actually, we could try a test run where we allow 3 attachments and see what happens. Okay, I think, okay, so now let's look at our GIF. So we have the cells are aggregating. The red cells are kind of trying to pull them out, and the blue cells are just kind of being dragged along, and that's it. Okay, so that's pretty cool. We have just a few more minutes left, but I think we have time to go to the stretch goal of adding more complex dynamics on this. But first, I think it's actually going to be really fun to go into our settings, and I want to play with, there's actually a fun question, right, about the maximum number of attachments and why 6, why 2. 2 in this case because we want to form chains, which might be nice if you were doing something like, say, angiogenesis. But let's change it for now, for the fun of it, to 3 and see what happens. So let's see what it does. Let's see what pops out if we just change the maximum number of attachments allowed. So here's my initial snapshot. Thing is already running. I'm going to go ahead and try to, I'm going to find one of my open command windows, and I'm going to go ahead and just remake that GIF, just so I can get some dynamics. But here's just 10 frames later. We have some that have formed yellow adhesions, and you got these little balls in some cases, right? Because this guy's attached to 3 cells. All 3 of these are attached to 3 cells. So you get this little tight ball, and this is going to be kind of a confused little entity here. Here we have kind of a ball attached to 2 ends, so that's kind of a fascinating structure. And then we have some that are, I think, going to be a little bit more Hydra-like. So we'll have to see what these things do. Let's look at the animated GIF. So they kind of come together. These guys are confused, but you see how these now are kind of, the 2 red ends are kind of pulling this thing out, and yeah. Well, it can form some kind of structure, and depending upon the number of agents, we could probably really get big variety of what's variation, what's happening here. Let's go ahead and kill the run and go on to, and basically we're going to iterate on this just a little tiny bit more. And I'm going to see if we can get a little bit more migration, a little bit more complex interactions here. Let's make sure we put the max attachments back down to 2, and then go back into the code. So if you run it, we got, here's kind of our expected behavior, just like we saw. They come together and form these chain-like structures, and then the red ends are trying to kind of stretch them out. So now let's change it. And what we're going to do is we're going to have chemical communications. This is basically juxtacrine communication across these attached cells. We're going to assume that they have some kind of a factor, a worm signal, let's call it a head protein or head signal that can diffuse along connected cell boundaries, like a juxtacrine signal. And we're going to model this, say that every cell has kind of a stochastic level between 0 and 1 of this protein. and that it basically is going to use a Fickian diffusion, so that if the cell you're trying to diffuse in has more head protein than you, then that's the wrong direction, and the approach is going to go in your direction. Just with a really, really basic, Fickian type of law here based upon the difference. So transfer rate times the difference summed up over all your attached cells, and that will be that. And if it's one attachment, we're just going to hold it fixed like a Dirichlet condition on this, basically one-dimensional diffusion. And so cell migration, we're going to change the rules a little bit, so that head cells are going to have that strong chemotactic avoidance like we had, because they want to avoid running into other worms, and they're going to be responsible for guiding the worms. The tail cells are not going to be really actively migrating, they're just going to be dragged. And the middle cells are going to basically sample the direction of that head signal, saying I have two neighbors, I have one way, upward way. One will have more signal, one will have less, just because stochastically they won't be the same. And that gives me the directionality towards the head, and I'm going to move towards the head. So we're going to get some kind of coordinated motion out of this based upon that differential communication. So we're just going to update setup tissue to give them a random value of the head. We're going to add custom data to our XML configuration file in the model builder. And we're going to add a little bit more complex work in the contact function to deal with checking against that head to say, am I ahead, am I tail, or am I in the middle, based upon that differential in the chemical signal. So let's go and edit the model. I'm going to add three things. I'm going to add head start, and transfer rate. And we'll give them values of 1, 1, and 0.1. So let's go into the model builder. I'm going to go to cell custom data. I'm going to add an attachment called a variable called head, which is like the head protein expression, I guess. Then head start will be the starting value for it. We'll just default that to 1, and one more called transfer rate, and we'll give that a value for now of 0.1. And let's just go ahead and save that. We already set the initial count to 500, so it's nothing to do. And now let's go into the code, and okay, we'll reload the commit into the custom.cpp, and now we have to go to the code called setup tissue. This is where we place all of our cells and set their initial positions and conditions. And what I want to do is I want to initialize the value of that head protein. And so right after I make my cell and assign its position, I'm going to modify the cell I just made. So I'm going to go and say that the custom variable for head will get a uniformly random distribute number between 0 and 1. And then I'm going to record that initial condition by storing it in head start. So I'm going to just copy it over. Okay, so we've got that. And then I'm going to declare some new functions for migration in custom agent. We're basically going to replace the old migration direction stuff with these new functions. Excuse me. So I'm going to go here into custom.h and get rid of these two migration ones and just add head, tail, and middle migration now. And this we're going to kind of race through a little bit, but I want to modify the contact function. So let me copy the code and walk you through what's happening here. So we go into custom. And we're going to go into that interaction function, the contact function. And rather than just returning right after the standard elastic stuff, we're going to add in a little bit more interaction. And we're going to say that if I have at least one attached cell, which you probably should if you're an attachment function, but that's okay. I'm going to try to figure out if I'm, the head or not, right? And I'm going to also try to figure out. Well, I'm going to just look. Actually, all I'm going to do is I'm going to sample the head protein in myself and my attached cell as part of my contact interaction. So I'm going to get my head protein value, the other cell's head protein value. So P other is going to be the cell I'm interacting with. And if I have more protein than them, then I am going to, well, that's funny. So I'm actually kind of doing this backwards here. If I have more protein than them, then I'm going to figure out my amount to transfer. Then I'm going to say that's going to be dt times the rate times the difference. And I'm going to remove that amount from me and dump that amount into the other cell. Now, I am writing the other cell. That's not thread safe. So I put in this pragma OMP critical here. But notice that since I made a convention saying that I'm only going to evaluate this if my protein is more than theirs, that avoids the double counting. Because if mine is more than theirs, then theirs is less than mine. So we won't double do this calculation. Okay, and there are probably more fancy ways we do it, but this is actually a pretty simple way to do it. So this is adding the diffusion of that protein across the connected boundary between the two cells. And now let's edit the custom function. You know what I'm going to do? I'm just going to completely replace it. This is a very similar one, but a little bit more elaborate in the logic. So let's go to the custom function here and just replace all this. So there's the first page of the function. Here's the second page of the function. We have just a couple minutes left. I don't want to run too late, but I do want to get through this because I think you'll get a kick out of it. So here I'm just going to say my custom function. I'm going to look for the signal in my environment, and so I know where it is. I'm going to look for cells to attach just like before and form attachments as needed up to my maximum number of attachments. And then I'm going to say, based upon the number of attachments, if I have no attachments, then I'm going to keep using chemotaxis just like before. If I have one attachment, I want to figure out if I'm a head or a tail. And so how do I do that? I query the head value in myself and in my attached cell, and I could do a comparison. If my value is lower than theirs, I'm not the head. If my value is higher than the other one, then I've got to be the head. And so I look at, my value, and I look at their value. So, oh yeah, I guess in end cells, I'm supposed to keep mine constant, by the way. So I'm going to use my initial value, and then I'm going to compare that to the other cell and just decide, am I a head cell or not? And then I am going to say that if I am a head cell, they're going to use the head migration direction. Otherwise, I must be a tail, so use the tail migration direction. And then if the cell has two more attachments, it must be in the middle. And so I'm going to use the middle migration direction. So the last thing to do is to add these migration bias functions. So I'm going to replace all the old ones with these. I'm not going to go through them in great detail here, but just know that they're more or less what we talked about, right? The head is trying to be very chemotactic away from the signal. The tail is kind of trying to follow along. And actually, the tail sets its migration speed to 0. And then if you're in the middle, you're actually going to say, I want to figure out who is upstream from me by comparing the two values and say that I'm going to follow the cell that has a higher head protein value. So the neat thing is that we have a diffusing chemical signal along the length of our worm. And by just comparing your signal to the neighbors, you know where you are in that worm. You kind of have local information that gives you a little bit more global knowledge in this chain of cells. So it's starting to act a little bit more like a multicellular organism. Let's modify the coloring just a little bit. What I want to do is only color the head cell as red. So let's find that coloring function. So that we want to be able to tell apart the head and the tail. So the head will be red, which means that the tails won't satisfy any of the conditions, they'll become yellow. And let's see, that should be it. So let's build this thing. So let's make it and run it. And let's just open up a couple snapshots. So here is the initial snapshot, just like before. 10 frames later, we have formed some chains. Now, notice that all these cells are still red, which is a little bit concerning to me. But let's go forward a few more. It might be that they just haven't been able to figure out if they're heads and tails yet. It takes some time for that signal to diffuse across the worm. Still hasn't told. So this is a bit worrisome for me. I might have some debugging in my example. It worked for me at like 2 in the morning, but let's let this keep going. Wait, did I recompile this? No, I didn't. That's why there's no change in behavior. There we go. Let's rebuild it and then run it. Okay, that should make more sense. So here's my initial picture. I've now got 10 frames, so I can see what's going on. Oh, they've aggregated in a weird way. So I've got something going on here. We don't have 37 frames yet. So they've aggregated, and for some reason they are not collected. So I've got something wrong with some of my rules here. So I will debug that and post up a code. I will say this is what's supposed to happen. So I will have to debug that later. They want to aggregate, and then the red cells start bossing around. So this one hasn't really been able to decide who's the head yet, but most of them do. And see how the red is leading it, and the yellow is kind of like an anchor. and the worms are trying to avoid one another. So that's kind of what emerges from that. I have one more question, or actually a comment from Caleb. Says, yeah, basically this would be not a bad start for an angiogenesis code. So that could be a fun thing to try out. And actually, I'm kind of itching to try it out too. I don't want to belabor it, so I will do my debugging on my own. We have a break right now, and then we'll come back.